Okay, so we continue on SI units. So we have learned about this. Alright, and then derive units. Okay, so this can be done by using base unit in equation that define other physical quantities. For example, derived unit of volumes is length power of 3. Means length times length times length. That will give a volume. Right. So for derived units, for example, area is equal to distance times by distance. Right. Distance times by distance, that will be m squared. Distance in meter time by meter, so m squared. Volume is length times by length times by length. Alright, that will be m cubic. Alright, and then density is mass over volume, kg per meter cubic. Alright, and then the velocity or speed is equal to distance over time. Distance is m over s. Okay, m distance is meter, time is seconds, so meter per seconds. Acceleration is distance over time squared, so time ms squared. Alright, and then force is mass times by acceleration. Mass is kg per meter, kg meter, and then mass is kg, and then acceleration is meter per square. Just now here, from here, right, so it's become kg meter per square. That would be equal to Newton, or the simplest units is N. Pressure is force over the area, kg per m per square, so that would be Pascal. Right. So SI also has prefix because the number sometimes is always too small or too big. Alright, so we put the prefix in order to make it more convenient for SI units to be complied. Alright, so prefix used to indicate the power of 10, for example gigahertz or megabytes. Alright, this example of the prefix used, so we have exa is E, 10 power of 18. Alright, that is hexameter is 1 time power of 80. So look at on the yellow one. So yellow one is the most prefix that we always use. For example, giga, the symbol is G, that is 10 power of 9. So 1 gigameter is 1 power time power 10 power of 9. Right, giga, mega, kilo, this is among the useful prefix. And then we have deci, centi, milli, micro, nano, and pico. Alright, start from deci, we have -1, so 10 minus 1, 10 minus 2 for centi, milli is 10 minus 3. Alright, and then micro -6, nano -9, pico is -12. So you need to remember all these. Sometimes it's asked about femto and also atto as well. So temperature normally is measure of the intensity of the heat. How much the heat is. Is it too hot or too cold? Alright, so units for SI normally is Kelvin, though we use Celsius, alright, for general scientific, but for standard international standard is Kelvin, K. Yeah? So Kelvin is equal to degrees plus 273.15. That will give a Kelvin, while Fahrenheit is 1.8 times degrees plus 32. This is how we find the Fahrenheit. Alright. So Fahrenheit, for example, freezing water is 32 Fahrenheit, boiling water is 212 Fahrenheit. This has to be remembered. While Celsius degree freezing point is 0, boiling point is 100 Celsius. Okay, next is precision and accuracy. How precise and how accurate our measurement is. So precise refer to how closely individual scientific measurement agree with one another. So accuracy refer to closeness of the average of the set of the scientific measurement to the correct or most preferable value. So we're going to see a figure later on where you can further understand about this. And then sampling error occur when a group of scientific measurement do not represent the entire population that has been studied. Alright, so this is an example of precision and accuracy. Alright, so this is the target. The red one, okay, this target, this is the dot. Alright, so this is the target. Alright, so if the arrow is far from the target, so it means that it has low accuracy, low precision. Okay, but if the sample are close among them together, though they are far from target, this is low accuracy because it's not come to the target, but it has high precision. Okay, they among themselves have high precision because they are closeness to each other sample. Alright, so now this showing that we have high accuracy because of all the arrows goes near to the target. Okay, near to the target, but somehow it has low precision because of the data. The sample itself are far among themselves. Alright, so this is high accuracy, high precision, where the target itself is made, and then sampling among themselves, there are closeness to each other. Okay, right. So look at back the meaning. So precision is closeness of each sample, where accuracy is means is meet the target. Alright, so significant figures. Significant figures is we know what significant figures is by term. It's all digit in number. They are known with certainty plus the first uncertain digit. So more significant digit obtain better precision of the measurement. Concept of significant figures apply only into measurement. Exact value have an unlimited number of significant figures. So these are among significant figures. This digit has some uncertainty, 24.3 degrees, because of the first two digits are known for sure, but at the back it's not. Because temperature, sometimes when we look at the thermometer, is it 2 or is it 0.3 or 0.25? So it's not certain. Okay, that's why we call as uncertainty. So this is when you have 1, 2, 3. So we call this one as 3 significant figures. Alright. This digit also have some uncertainty because it could be 0.33, 0.22, 0.32 or 0.31. So there are 3 digits are known for sure. This is known for sure, and then we have 4 digits here that can be seen. So this is called as 4 significant figures. Right, rule for counting significant figures are like this. For number 1, any digit that is not 0 is significant. So like the number, there is no 0 here. So 845. So this is called as 3 significant figures. So in this number 1.234, there is no 0 here. So they are all significant. Okay, so we have 4 significant figures here. Okay, if you have 0 between the non-zero digit, they are significant. Like 606, this 0 is significant, is counted. So we have 3 significant figures. If you have 40,005, okay, so this is 0 between the digit, between the non-zero digit is counted. So we have 5 significant figures. Alright, 0 to the left of first non-zero digit are not significant. Okay, 0 to the left of the first non-zero. Okay, this is the first non-zero, which is 8, and then this 0 to the left is not significant figure. So how many significant figures only counted here? Only 1 significant figures. Alright, so this is 2 significant figures here. Okay, rules number 4. If the number is greater than 1, then all 0 return to the right of the decimal point is counted as significant figures. Okay, number greater than 1. For example, 2.0 mg. So this number is counted. Okay, so this is significant. So 2 significant figures. Okay, this is more than 1. So 3.040, this is 4 significant figures, is significant. Right, if number less than 1, then only 0 that are at the end of number and 0 that are between non-zero, there are significance. Okay, look at this one, 0.09, less than 1, isn't it? Alright, and then it says then only 0 that are at the end is counted. Okay, this is only this 0 is counted, this 2 is not counted. So how many significant figures? Just 2 significant figures. This one, how many significant figures? Only this 4 is counted, while this one is not counted. So 4 significant figures. Right, so number 6. For number that do not contain decimal point, zeros after last non-zero may not be significant figures. So this one, it doesn't have any decimal points, so 0 after last non-zero. Okay, 400, only 4 is counted, so that's why it has 1 significant figure. Alright, 2 significant figure in 40. Alright, and then this one, 3 significant figure here. Okay. Okay, in this one we have 3 significant figures, sorry. So by using significant notation, we can express number 400 as 4 times 10 power of 2 with 1 significant figure, or 4.0 with 2 significant figure, or 4.00 with 3 significant figures, because we say that number that larger than 1 and then it has 0 on the right after it, it has decimal places, it counted, it's significant. So this is 2, this is 3, yeah. Okay, so expressing significant figures, correct. So for example, measurement, this one, 25 gram. Okay, number of significant, how much the significant figures here. So I want you to answer this in your notes. Okay, 0.03 kg. So answer all of these, how much significant figures that it has. Okay, you may check later. Okay, so I want you to answer this one as well. Determine the number of significant figures in the following measurement. Okay, and then we're gonna learn significant figure in calculation in the next video.